Okay, hello everyone. I'm Elahe Soltanagai, professor at the University of Illinois Urbana-Champaign, and we're kicking off the morning session on removing the wires. It's my pleasure to actually start the session by introducing my own student, Ryu Akubo, who's a master's student at UIUC, and he's graduating this semester, and he'll be presenting the work on integrated radar, two-way backscatter communication and sensing. And yeah, let's kick off the session.
All right, good morning, everyone, and thank you for Professor Elahe for introduction. My name is Ryu, and I'm a graduate student from University of Illinois Urbana-Champaign, and today I would like to give a talk about our latest work, Backscatter, which is integrated radar two-way backscatter communication and sensing with the low-power IoT tags. So this is a joint work with Luke Jacobs and Professor Elahe, also from University of Illinois, and Jinghua Wan and Professor Stephen Bowers from University of Virginia. So to begin with, let me first give a quick introduction about the radars. So radars are known as a strong sensing device that is widely adopted in many applications, such as the cruise control systems in the vehicles. So radars has several advantages over other sensing devices, such as the optical sensors, as it can work with any weather or lighting conditions, and it can penetrate through the objects and obstacles. And at the end, it is capable of sensing the environment with low power. So nowadays, the radars are not only limited for the cars, and it is also applied in many IoT applications. For example, such as the radars equipped in the robots in the factories, and it is also used in the drones in the smart warehouses. And even in the smartphones, in Google Pixel 4, we have a radar embedded in it used for gesture and posture recognitions. So with the radar being such a powerful sensing device, the question is, how can we enable the radars to add the communication feature on top of it in favor of its low power consumption? All right, so that leads us to a backscatter communication on top of the radar using the low power backscatter tag. So usually in a backscatter communication, the radar will send a carrier wave signal, and on the other side, we have a receiver backscatter tag that is operating in two different modes. So when the tag is on, the tag will reflect all the signal received by the radar back towards it. And on the other hand, when the tag is off, there will be no signal get reflected back towards the radar, as the tag will absorb all the signals. So what we usually do is we switch between this on and off mode, which will effectively reflect and modulating the signal back towards the radar. And at the radar, we can use the on and off keying to decode the information sent by the tag. So there are a lot of previous work that tried to integrate this backscatter communication on top of the radar to enable the communication from the tag to the radars. However, the communication from the radar to the tag is relatively unexplored. So this limits us from having the two-way communication link between the radar and the tag. So why do we even care about the two-way communication? So I think having two-way communication can enable a lot of interesting application. And here is one example. So taking this smart warehouse case as an example, let's say you have a radar equipped on the drone that is carrying the assets. And let's say we have a tag inside asset boxes or simply equipped on the robots. And in this case, the radar on the drone are not only used for sensing the environment, but it can also use to read or write the information to the tag. For example, you can mark the asset as a fragile item, or simply you can write the commands to the robots and telling them what is the next task to do, and so on. So here one big advantage is that these tags can operate in low power fashion, which is quite important when the overall power supply is limited. So in this work, I would like to present the Backscatter. Does it show up? Okay, I'd like to present the Backscatter, which is the first radar backscatter system that enables the simultaneous two-way communication and sensing. So Backscatter has three major modules. Backscatter has three major modules. First, it is downlink communication from the tag to the radar. And then it is uplink communication from the tag to the radar. And then at the end, it is a localization of the tag using the radars. So let me first talk about the downlink communication first. All right. So in Backscatter, we need to overcome two major challenges to enable the downlink communication. So first, how can we encode the bits on top of the commodity radar waveform without losing its sensing features? And second, even if you can do that, how can we decode that at the tag while keeping the low power fashion of the tag? So before going to the details, let me show you how the actual radar waveform actually looks like. So in Backscatter, we use a type of radar called frequency modulated continuous wave radar, which is usually called FMCW radar. And this type of radar is the most commonly adopted radar in the industries. So in FMCW radar, it will transmit the signal, and as the signal hits the target object, we will have a reflection from the target object back to the radars. So in this scenario, the signal received at the radar will experience some delay, which is caused by the signal to travel through the air and coming back. And at the radar, we will process the signal by mixing them together, and we will end up getting a constant tone signal called IF signal, where the frequency is equal to the difference between the transmitted signal and the reflected signals. So one key observation here is the frequency of the IF signal is proportional to the range between the radar and the target object. So by analyzing the frequency of the IF signal, we can easily estimate the range between the radar and the object. So back to our original question, back to our original question, how can we encode the bits on top of this FMCW radar waveform without losing its sensing features? So to answer that question, we looked into multiple parameters of the FMCW waveform, and we found the easiest to leverage is the chirp slope. So therefore, we propose a new modulation scheme called chirp slope shift keying modulation, where the different chirp slope will carry different bit symbols. So here, for an example, the bit 0 and bit 1 has two different chirp slopes to get allocated. So let's take a look at how we decode this at the tag. So one naive solution will just try sampling all the chirp signals directly and reconstruct them to calculate for the slope. But the problem here is the sampling rate. So for example, if the radar is operating in like 10 or 24 gigahertz, which is actually the common frequency that the radar are operating in, we would need even higher frequency to sample these signals, which will end up consuming a lot of power. So instead, in Backscatter, we designed a low-power decoder that will bring the frequency down to sub-kilohertz level for analysis and decoding. So in Backscatter, upon the reception of the signal, we split the signal into two lines with two different delays applied to them, and then we mix them together. So after mixing, we will get in a constant tone signal where the frequency of this signal is proportional to the slope of the chirp and the amount of delay we apply to them. So one key point here is that since the amount of delay we apply doesn't change, and we know the amount of delay applied to them, so we can solve for the slope. By looking at the measured frequency of these tone signals. So by analyzing the frequency of this tone signal, we can easily decode the bit symbols on top of the FMCW radar waveform. All right, so putting everything together, here is the entire tag schematic, where we have the decoder module we just explained, and we also have an integrated uplink module for enabling the backscatter communication, and we also have a retro-reflective two-antenna structure that will boost the reflection from the tag. So to see the entire operation, we have a radar sending a sequence of modulated chirps, and the tag receives and decodes it, and at the same time, the RF switch and the uplink module will modulate the signal, and we will reflect it back towards the radar, and radar will see the signal from the tag to identify and localize it. So, but here one question you may have is if the change in slope will actually affect the localization. So the answer to that question is yes, it will. So here is the visualization of the IF signal received at the radar after mixing. So as you can see, you can kind of see the tag reflections here, but you see the frequency is fluctuating a lot. And this is because the changing the chirp slope can cause the ambiguity in the frequency of the IF signal. So, but fortunately, since the radar knows all the configuration that that they are sending, so we can apply a software correction to reduce these ambiguities. So here is the comparison between before and after the software correction we've made. So now you can see that exactly where the tag is located, and we can also see the tag modulation more obvious now. Right. Then let me define our packet structure for synchronizations. So in Backscatter, the downlink packet consists of three major parts. That is header, sync bits, and data payload. So header are the sequence of four fixed slopes, and we use it for packet detection and determining the communication mode. And more importantly, we also use it for estimating the chirp duration and the bit size of the packet. And then it follows by the synchronization bits, which is also two unique slopes, one unique slopes, and it is used for identifying the start of each chirps, and it is also used to identifying the start of the data payload as well. Then it follows by the actual data payloads, where the bit symbols are encoded as different chirp slopes. And one observation here is that we can increase the data rate by simply increasing the bit symbol size, and that is just adding more variation of the chirp slope on top of it. Right. So so that is the overall features of the Backscatter. So we introduced how we encode the bits on top of the FMCW radar waveform, and we also introduced how we can decode that information with low power fashion using the two delay lines with different delays. So, okay. All right, so for the interest of time, I am not going to talk about the uplink communication and localization in detail for now, but it is explained in detail in our paper. So if you're interested, please refer to our papers. So now I would like to quickly walk you through with the evaluation of our system. Right. So in our evaluation, we use the off-the-shelf FMCW radar, and we also custom built the Backscatter tag using the off-the-shelf components as well. And we tested our performance in the indoor environment, and we measured the bit error rate as a we measured the bit error rate to show the performance of our system. So first, we evaluated our downlink performance by measuring the bit error rate over different symbol size and bandwidths. So here, the brown bar plot shown here, we use is a 250 megahertz, and as you can see, as the symbol size increases, the bit error rate also increases. And this is quite expected, because as the symbol size increases, the two adjacent chirp slopes are getting closer and closer. So we also tested this with two other bandwidths as well, and as you can see, the higher bandwidths can compensate the bit error rate, which shows the Backscatter's performance of having a high data rate while maintaining the low bit error rate. So we also evaluated our system with the varying distance, and as the plot shows here, our system at 40 kilobit per second, our system works up to 7 meters with under 0.1% of bit error rate. So we also tested this with two other data rate as well, and as you see, the slower data rate generally has lower bit error rate. And one thing I would like to note here is this is a downlink data rate, and while the number looks too low, but we consider this is enough, more than enough for IoT application, where the downlink is usually just used for writing the command to the tag or simply just setting up the tag. All right, and then we also evaluated the localization performance, which is just radar localizing the tag. So we compared our system with our baseline, which is the radar sending the fixed chirp. And as you can see from the plot, our system has a comparable performance with the baseline, where it operates up to 7 meters under a 10 centimeter of accuracy. And then, and then we also tested our system in 2 different bands, 9 gigahertz and 24 gigahertz. And as the plot shows, we also get the comparable performance between these 2 different bands, which also shows the Backscatter's performance or potential of operating in higher frequencies. All right. So yes, so here is the takeaway of this presentation. So we presented the Backscatter, which is the first integrated 2-way radar backscatter system that uses the low-power IoT tags and off-the-shelf radars. And we also proposed a novel chirp slope shift key modulation to encode the information on top of the radar's waveform. And we also proposed the low-power decoder module to decode that chirp. And we also evaluated our system where the Backscatter achieves up to 50 kilobit per second under the 1% of bit error rate up to the distance of 7 meters. And we consider the Backscatter opens up a new research avenue towards the integrated radar sensing and communication, and we think there's a lot of opportunities of future works. So for example, extending the Backscatter system to multi-radar and multi-tag setup, and that followed by the design of the new MAC layer protocol design on top of the radars. And at the end, more importantly, assessing the network throughput is also the new space of improvement of the Backscatters. So that is all about the presentation. Thank you for listening.
Yeah, my name is Takuya Fujashi from Osaka University, and thank you for your presentation and interesting talk. I am have a question about your localization error in the figure. So I do not understand why with the communications scheme can decrease the localization error against without communication. So it means the uplink or downlink communication may send something helping the data for enhancing the localization performance?
Yes, so thank you for the question. And so to answer that question, first, I will say that the localization performance between so with the communication and without the communication, actually the performance is not that different. I will say with a larger statistics, it may end up having the same accuracy. And also one possibility we have is since we are using the different amount of chirps for the communication, so maybe that can bring the error down a little bit. So by averaging, because we have different measurements, so by having the average of them, we might bring in the error down to a certain level with having the communication.
Okay, thank you.
Julie Chen from University of Minnesota. Really nice work. So in your kind of two-way communication part, so one of the things you said you want to use for example, radar, whatever the system to write command on the tag, etc. So one of the questions, since you have a potential error rate, right? So do you actually design some kind of parity on the CRC to ensure the command being received correctly? Otherwise, you're going to write the wrong kind of command, right? So I know this may be part of your MAC design scheme, right? So how do you actually look into this feedback, right? So you have to do ACT to say, hey, you're getting correct command because you don't want to write the tag incorrectly.
Yes, thank you for the question. And I think you're talking about the higher level MAC layer design. And so our work is like focused on the more like physical layer design, and we haven't really like go into the higher level design of how we can like do the acknowledgement command. So I think we leave it as all the future work of building the MAC layer design on top of it. And I think there's a lot of space of improvements there. And yeah.
Right, so I'm kind of curious whether you have some sort, for example, could you, instead of using standard ACT, you just act back the signal since you're the radar, right? So then that's the way for check to say, hey, whether radar can check whether you receive the command correctly. Just a thought.
Yeah, thank you.
Hello, I'm Zheng Guoshi from the UNSW. I have two short questions. The first one is that for your experimentation, is considered the non-offsite scenario or non-offsite scenario for the communication and the localization.
Sorry, I didn't get your question. Can you repeat that?
You consider about a non-offsite scenario or non-offsite scenario? Is some object between your receiver and your radar?
Sorry, you mean if there's an object with...
Yeah.
Are the accuracies you have presented only for line of sight, or you have considered
Line of sight?
non-line of sight, like being blocked by?
Oh, I think it's not getting blocked by anything, but it is an inside door environment, so we consider there's a lot of multipath and a lot of like interfering noise. And I think when I collecting the data, my lab teammate was collecting the data for other experiments between like next to me, so maybe some interference. But yeah, that's the setup of the
Okay,
data
thank you. And the second question is that I see you have different configuration of your radar, and it's the one-time configuration, or you need to regularly change it because you design different chirp slope.
Yes. So yeah, that is one-time configuration that you need to tell the tag, or you need to write the information to the tag, like what chirp slope that radar is actually sending, and you need to have like a 1-to-1 relationship between the chirp slope and the bit it is sending.
So at your radar side, you hack them to write different.
Yes.
Okay, thank you.